It's great. So we're now live on YouTube, so that's working. Make sure the sound is working there. It's great. So we're now live on YouTube. Okay. So let's get started. So they changed the interface on so Zoom again. So I can't necessarily tell if you're raising your hand for whatever reason. I think I can. Let me see if I can still see the chat. What happened to the chat window? Yeah, so if you still have questions, you can just do stuff in the. So okay, so if, someone clapped. Okay, great.
Yeah, you can use the reactions at the bottom, and I think you should be able to see that. There's like
yeah. So you can use the reaction at the bottom. So good. So so typically in the past it would elevate all the raised hands. I can't. The interface is different. I can't see all those as easily. It doesn't move into the top of the list of people. So if you have a question, if you put in the chat, that'd be great. I think I can see everything in the chat as we're going. Yeah, so great. So let's get started. So let's see. So let's quickly look at the schedule before we get going. Let me move that up there. Okay, so so we have 4 lectures left, including today. We basically finished with everything in the dimensional reduction. We're going to do kind of a lecture on privacy, what to think about privacy and data. We're not going to be able to get into anything too terribly specific, but I'm hopefully give you an overview of this area and kind of what people have done in the past, inform what are a bunch of the pitfalls, and kind of what is the main technology that people are using now. So homework 7 is posted as due next Wednesday. So there's been a lot of discussion on Canvas. That's great. So if you have any more discussions, please post there or kind of visit us in the virtual office hours. Homework 8 will probably post that. So like later this week. I think probably after the Wednesday lecture, you could probably get started on it. It's due on April 22nd, which is like the reading day. If you want to turn in later, just please let me know. I'd rather have a fixed date that you try and finish it by, and that date has seemed to work kind of well in the past. So the other thing looking forward on the calendar is the end-term test. The end-term test will cover everything after streaming. So starting with regression. And so it won't, it's meant not to cover the first part of the class. Now there might be a question from there that because it kind of is how that something from some L2 distance is useful in some contexts that we covered early on, but that should be fair game. The main point is to test this stuff in the second half of the semester. So, all right. So I've left it on that date. I didn't want to try and squeeze too much more information in the semester by moving it. We're obviously not going to have it in the classroom. I'm finalizing plans of how to do it. I want to try and make this as flexible as possible for all of you. And I know for a number of you, this is a challenging time. So I will post some details of how we're going to do it by by like the end of the week. I'm planning to roughly, the plan is, unless I change it to hear feedback, and I've heard some feedback, which is great already, to have it roughly be a take-home test, probably be 80 minutes time, but over that window still where you would take it on Monday, April 20th. You know, roughly a 24-hour window. If there are times in that window which are much better, like you'd rather have time Sunday night or Monday night, please let me know. I know some of you have had your schedules flipped upside down. I certainly have. So if you would rather have a certain time window when you can take the test available, please let me know. But the details on how that will work, I'll post something by the end of the week. Still investigating a couple of options, but I'll probably be as flexible as I can on this. So okay, and then after today, we're gonna have 2 more lectures, the Markov chain and the PageRank. I think these are kind of core lectures in the graph analysis section. And then there'll be 2 things on map reducing communities. I've listed as the last lecture. If you have feedback you'd really like to see, well, one thing we can do now is if you'd really like to see MapReduce or communities, if you can, let's raise your hand if you'd much rather see MapReduce than communities. Okay, and on the other hand, if you'd much rather see stuff on different types of how to find communities in social networks, raise your hand. Okay, so I see a few more hands raised for the communities and social networks. This is probably what I was planning to do. I'll probably try and merge a little bit of the MapReduce into the PageRank lecture and a little bit into the communities lecture, but try and focus the bulk of time on communities and in social networks is the plan. Yeah, so, but if I hear feedback, I know some of you are not watching this live, feel free to give me feedback and I'll kind of adjust on the fly. So, okay, so any other questions? Oh, and the other thing is the final report will still, I've shifted that back a little bit. It's now due on Wednesday, the 15th. And then we'll still plan to have a poster session. I haven't really figured out exactly how we're going to do this yet. It'll somehow be online, but I still want to have some interactive nature to it. So I will post those plans later. But any other main questions now before we get on with the lecture? Great. All right. So let's talk about privacy. So, okay, so you could have, their entire classes on ideas of privacy and data. There's lots to cover here. And so I'm not going to be able to cover everything. So we're going to kind of go through a little bit about the history of what people have tried to and where these pitfalls are, and then kind of talk about some modern approaches with differential privacy. And so the first thing I want to kind of enforce in your mind here is that there's part of the issue of privacy is there are ways we can guarantee certain things about kind of when we are working with or using other people's data or releasing data, and some of these questions are sometimes enforced by law. So with medical data, there's a lot of law out there about when you can release certain types of data. In fact, I think a lot of people have been a little bit fast and loose with this law, with these law over the last few weeks, because of the many attempts to try and get to the bottom of the COVID-19 situation. But so I think these laws are, but in other situations, there really aren't any actual laws. There are there are kind of these user agreements that companies have when you sign up about what they'll do with your data. And how these are enforced is kind of a gray area, and it changes over time depending on which lawyer is or judge is deciding about these things. And these contracts are shifting over time. And there's a lot that goes into this that has to do with kind of, there is some law, there's also some designing the policy. And a lot of us won't necessarily have impact into that. There might be some of you who go into kind of the policy aspects of this, but most of us will be dealing with it as a user of this data, maybe working in these companies that have access to this data. And so I'd like you to think of this from the perspective of what's the ethical thing to do here, right? There's going to be guidelines your company has hopefully put together on what to do, and try and respect those guidelines and so forth, but there are going to be gray areas. And okay, so it's not my, it's also not my place to tell you what is ethical, what is not ethical in this situation. I certainly have my own opinions, and if you ask me outside of my role as a professor, I'd be glad to tell you about those. But as my role as a professor is not to tell you my ethical views on these things, what I would like to do is to try and equate ethics with some notion of empathy. Okay, so just to explain what are the ethical dilemmas, and you can decide for yourself. I've come to certain conclusions that a lot of people who've looked closely at these have come to similar conclusions, but then but not everyone, and that's up to policy and law to some extent design, but for you to individually keep this in mind. And so my view is you should think of this as the empathy, where you should kind of be thinking of what if you were the data point. Okay, so we're often thinking about the dimensional reduction and regression. We're thinking of this, the data is this matrix A, and each row in here is AI, right? What if, let's see if I, what if this, was, so what if this was you? So, okay, so one of these issues, we've talked about some of these issues before. They're making automated decisions based on data, including your data, or maybe it's been trained on other people's data, but there's going to be a prediction made on your data, whether you get a loan, whether you get accepted into graduate school. And part of this is automated in a way based on these decisions. Hopefully not, but what if you're in jail for some reason and you're going to be put out on parole or not? There's a lot of automation that goes into the decision. It's not completely automated, but judges will get kind of these predictions, and they can use that towards making their decisions. So should they do that? We've asked those questions earlier in the semester. I want to ask you a different question in the privacy section. Is if there was so a lot of these, for instance, one of the ways to try and make the decisions based on parole more fair is to try and put out the algorithm that's used based on the training data. But then to understand it, you need to understand what is the training data. Would you like it if your data was put out there so this was completely transparent? What maybe perhaps biases were in the training data? Okay, and so I want to think, if this was your data, would you want that information out there? Okay, maybe with parole, that's hopefully none of you have to go through that, but it could be with kind of hiring decisions, with loans, with admissions into undergraduate or graduate programs. These are all things that you might not want all of your data out there. With kind of undergraduate degrees, there's all these HIPAA issues that we can't kind of give out information about which courses students took, what grades they got in this course without your permission. And for instance, with Zoom, there's a lot of discussion. Could we use Zoom? Was it compliant with HIPAA? I'm not supposed to discuss any of your individual grades over Zoom was what it was decided, but the rest I could do. That wasn't a violation, but it's effectively an open classroom the same way our classrooms on campus used to be open. Okay, so what if this was you? Think about the release of data. Think of if that was your data, would you want that released? I think that will guide you towards at least the fair decision that you're ultimately going to make. So the rest of the lecture will be going through some actual scenarios to try and help you kind of see, how the data mining techniques that we've discussed and some a little bit kind of outside what we've discussed, how these will kind of can interact with these decisions. All right, so to give some context of this, like a lot of you for your projects are looking at these data sources which have been placed online. So in the I would say the early to in like the early 2000s, there were a lot of like these new tech so there were a lot of these new tech companies, and these tech companies were doing well, and they were the first to really automate the collecting of data of people. And so there was kind of eagerness to get engagement from people in the public to use their product, to make the products better, but also to interact with some like scientists and engineers. So one, they wanted to recruit people to work on it, interface with open source programs, but also kind of get people in academia to try and develop techniques for these problems. And to develop techniques for the problems, they need to know about those problems and understand this is the really big thing we need to solve. How do we make this sort of prediction? Okay, and so there was a lot of eagerness to do this, and actually a number of the data sets that I linked to in the DataMine project proposal kind of document are kind of, some of them are older data sets because that's when they were released. They were kind of this, companies became much more hesitant to put data sets online starting about 10 to 15 years ago. There was a period where there's excitement, and then they kind of slowed down because of the number of events we'll talk about this lecture. All right, so kind of the context I want to think about is you're a company and you'd like to put kind of, so can we place a data set online, and we want to somehow anonymize this data set so that we can't tell who the individual people are. Then kind of state a goal, like a prediction of some point, find clusters, do some regression prediction on how much money someone will spend on my website or how much use they will get out of this product. And then, like have a, so have like a competition to solve it, right? So there's Kaggle's out there and does a lot of this now, but the data sets are kind of, there's a lot more introspection that goes on before these are placed online. Before they would say, look, here's a dump of our data, go at it, try and figure out what the most interesting thing is. They're much more hesitant about it. And it's because this idea of anonymizing this data is not as easy as it seems. And this is the issue with privacy and data, right? How can I try and solve some challenge or release a data set so a lot of people can work on it without revealing the stuff about the individual people involved, the individual data points. All right. And, you know, a deeper question we'll kind of get a little bit at, but, you know, is being asked kind of has been studied is how can I build a model that makes a prediction, right? So, you know, if I do this internally, let's say I don't release a data set, but I release a model, you know, and this is able to make predictions based on the data. It's trained on data. Does this give away information about the individual data points or not? Right? If I can make a really good prediction, so let's say I want to predict what someone's salary is, okay? And the prediction engine puts in their name and it predicts their salary. And if my name is in the training data, you type in my name, it predicts exactly my salary because it's trained on my data. That clearly that model is giving away my salary information. Okay. Would you want to use names for that? Well, that's the question we'll kind of get into a little bit in this lecture. We've touched on that as well. You might, and there's connotation carried in names for good and bad, right? Yeah. So okay. So these are kind of the context here. All right. To set the stage a little bit more, I'm going to tell a couple of stories in this lecture. And let's see, the first one is let me get that cursor off there. Okay. So the first one had to do with in the year 2000 or so, the state of Massachusetts, they have a lot of great universities there, said, we're going to, in the idea of openness, we're going to release everyone in the states their medical records online so that so that we can so that kind of people can study the information. It's enough different medical information that in aggregate you should be able to make predictions, learn about kind of different connections based on kind of covariation between treatments and diseases and so forth like this. And around 2000, people are very excited about this sort of idea. A number of you are working on this where you've gotten access today, but had to jump through a lot of hoops. They put a lot of the stuff online in the hope that a lot of people would use this, right? But they're worried about the kind of anonymization. They didn't want to put names on there, right? So they wiped all IDs, but they kept things like the zip code, the birthday, and the gender, right? So there are various things that were kept, including these traits. Zip code, you could maybe where they were in the state in case it was kind of localized, birthday to tell something about age, and then the gender in case it affects females and males differently. These seems like traits you'd want to know to understand kind of this medical information. Okay. But it turned out at the same time, and this is some version of this is true in most states, that you can buy data about who voted in the state and cost some nominal fee, like it was $20 apparently at the time. And this includes things like zip codes, gender. I don't know if it had the gender, but it had, well, I forget what it, maybe there's a typo in here, may have been gender, may have been the age of the voters, and also their names, right? So it had the names of the people as well. But it didn't say how these people voted, so that was okay. It just said who voted, right? This is still typically available in most states for some nominal fee. Okay. Okay. So as you can guess, what may have happened? There was a grad student at the time at I think she was at UMass Amherst, she decided, hey, this is, I think this is a problem. She realized these two data sets were out there and kind of combined them together and was able to do certain things like figure out what I think she was pretty confident enough so that she was able to determine the health records of the governor of Massachusetts. That's one of the state employees, because there are only so many people with that zip code, and I think age in because the zip code was restricted, and was able to pretty much figure out what were the health records of like the governor. And the story I've heard, I don't know if this actually happened, but that she actually sent the governor's information to him in the mail, right? As a way of kind of demonstrating that maybe there were some issues with releasing all of this information, right? So now Dr. Sweeney is teaches Harvard and has in fact done lots of pioneering work in this area of understanding privacy of people when this data is released in various ways. Right. So okay. So the kind of what's happened here is that they released some data set that they thought was very useful scientifically, and it's definitely is of interest scientifically. But they thought they'd anonymized it, but because there was this other data set out there, they were able to cross-reference it and kind of figure out like what was going on, get the exact records of some individual people, right? So this isn't great, right? So what happened after this is there was a kind of a series of approaches to try and understand how can release data anonymously that's still kind of so it kind of hid the okay, so how to release data anonymously while preserving individual info. Right, so there's a question. All right. So do you want to comment on open source intelligence tools used by companies and governments to gather data based on combining data with multiple public available data sources? It seems like cross-referencing data has become its own market. So yes. So great comment, great question. So yeah, so there is now, so the data itself has become very valuable. There are a lot of companies that kind of, one of the most kind of useful things they have and gives them an edge is having data about their individual customers. And what you'll see sometimes is a company will go bankrupt and get sold to another company, and all they really want is the data of the company. They don't want their technology or anything like that. They just want the the actual data. If you're watching anything now on like Westworld, I guess it's the data they're after now in some side of Westworld, right? So there's this market on data of people. So and there of course there's this company, there are these markets of trying to do this, like Facebook and Google. One of the reasons they're able to be so successful is that they can target ads because they've acquired a lot of different data sources about people and figure out how to use that in ways which is intelligent. Google has apparently some pretty good guidelines internally from what I've heard both externally and from people internally about not sharing data across different parts of the company. So for instance, Google Gmail doesn't use other sort of search data from you usually, I think, unless you search inside of Gmail. Facebook, I've heard less about this, but this is really how they're able to capitalize the most on this sort of stuff. Yeah, so these companies which are just trying to trade in data. Yeah, so yeah, it's now a market out there for this sort of stuff. And yeah, so I think this sort of stuff is pretty much here to stay as long as there aren't laws passed about it. There have been a lot of new laws coming on the books, especially in Europe. Europe recently, I forget the names of these laws, but there's been some laws coming on the books in the last maybe year or so that have really restricted the right to collect data, and companies must give users the right to delete their data. It's hard to delete data from a model or other systems, so this becomes problematic in that they have to allow the ability for it to be deleted, and this has restricted what they can do. And I think the European laws have teeth in them. And this hasn't so much happened in the US right now, but this sort of law is allowing some companies to be sued for pretty reasonable amounts of money. I think they're, in some cases for companies, it's still worth it to try and push the boundaries because they're worth so much that even $1 billion might be worth the risk. But this is going to continue to be an issue, and I think whether these are going to exist or not is going to depend on laws. Unless there's a law preventing this sort of stuff, it's going to keep happening. Yeah. So okay, so let's see if we can read what I wrote here. Okay, how to release data anonymously while preserving individual info. Right. So in the early kind of 2000s, there are these models that came out trying to say, how can we do this? And kind of the first model was called Canon Emma T, and the idea was so data set has kind of these has like these public traits. These would be things like possibly age, kind of like zip code, like gender, that like if you were to meet someone, they wouldn't feel kind of necessarily weird about giving this away. Maybe not age exactly, but could put me into an age bracket, right? Am I between 30 and 50? Yeah, so I'm between 30 and 50 somewhere, right? So that's probably obvious from looking at me that I'm in this age bracket, right? So the idea was these traits are categorical. Okay, so each thing was placed into a bin. Age is in a bin. Zip code is there a whole bunch of people with the same zip code. Gender, more or less, is the whole people are kind of in these bins, and so it doesn't necessarily identify something specific. Okay, and so there are also these like private traits. Okay, so like if someone if someone has cancer, right? This is probably like not as good to reveal. I don't think people necessarily want other people to know if they have cancer. May affect their hiring in a job. If the CEO of a company has cancer, then like when Steve Jobs had cancer, they tried to hide this information because the value of the company depended on Steve Jobs' health, right? So that they were not upfront about this information, right? So if his health records had been released, the valuation of the company probably would have been lower, which probably would have made sense. He was very influential in there, right? So, or maybe if someone has COVID-19, right? So for some people, they might not want people to know that so that they have it, or if they're exposed. Probably for public health reasons, it's probably good to know who has it and who doesn't. But kind of an individual, might not be interested in sharing this information, right? So the idea was that if we release information and we enforce that at least each kind of person has at least, say, k minus 1 other people with the same publicly released of the traits. Okay, so of the public traits which are released, so let's say instead of releasing everyone's zip code, gender, and so kind of and their age, right? I'm going to bin these in such a way that I maybe make the bins bigger if I want to ensure more anonymity. That for instance, the governor of Massachusetts, there must be at least let's say at least 10 other people who have the same zip code, gender, and like the range of their age. That way, if I'm able to kind of cross-reference this with the voter information, that might be the governor's health records, but it might be one of 9 other people who have the same health records. And so you wouldn't specifically know if they had, if they were their health records or if it was someone else, right? So this was the idea of k-anonymity, right? And so this was like a reasonably good idea at the time. It's the first idea that came out, but this doesn't always work. So for instance, I mean, this is still used in a lot of places. Like for instance, in teaching evaluations, if I teach a class and fewer than 4, I think total students reply, teach some seminar classes that are like this, that maybe there are 10 people and less than 4 reply, then I don't get any feedback or any individualized comments, because there's too good of a chance they think I'd be able to identify who it was who was commenting on this, right? Who like, let's say if I got a comment that someone thought that I was very smelly or something like that, then maybe I could guess who that person was, and then I would hold this like grudge against the person in future interactions. But if there were a lot of people who replied, I wouldn't have a good enough guess of who was the actual person making the comment, so I wouldn't hold this grudge, right? But was a possible problem with this. This doesn't solve everything. The issue is if everyone who commented in the class, everyone said I was smelly, then I would probably feel the same way about everyone in the class. I'd hold a grudge against them or something, and probably I should probably do something about the odor. If everyone said I was smelly, it's probably true, but it's virtual, so you can't tell. But if in the case of the medical records, let's say there were 10 people in the zip code with roughly the same age range and gender, and they all had cancer. Well, then I release it. I still know the governor has cancer because everyone in their anonymous group had cancer, right? So there was this kind of series of things, and so the next one was called L diversity, which was K and anonymity. Okay, so I still needed that every group I released had at least K had at least K people in this group of people could be co-identified, could be one of these K people, and each group had an L diverse traits. traits. Okay, so so what does this L mean, or L, well separated classes? It means, you know, so it has to say something like has there's some technical definition of what this means, but it's going to say example, some have cancer, some don't. Okay, so I'm going to have like two classes of traits, and so that in case one of them is bad, I'm going to have 10 people in here, and some have cancer, some don't. So I don't know if I can't know they all have cancer just because they're in a group where there are K people. I don't know which one, but they all have cancer. Now, with the L diversity kind of restriction, I can't release data unless they also have diversity within the groups as well. So that means I need to kind of increase the age brackets a little bit bigger, or increase the combined together zip codes in some way so that there aren't any kind of groups identified that all have this similar trait. All right, so then, all right, so this was, you know, this still doesn't completely solve the issue, because it could have been that, you know, there could be still an issue that they say that there are two groups that they either have cancer or have diabetes, right? So let's say that there are two very diverse groups, but one group, you know, has cancer, the other group has no cancer. One group has diabetes, the other group has no diabetes, but these are split. So they're still two kind of classes that are both somehow information you don't want to share. Just because they're diverse classes doesn't mean that they're actually it's safe or fair or good to try and release this data. All right. Okay. So this kept going, and then there's this other approach called T closeness. Okay. So and so this has L diversity. Okay. So that means it has canonymity. It inherits canonymity, inherits L diversity. So there's at least K people in a group for some parameter K. There's some notion of this group has this group of at least K people has at least two or, you know, these more different classes, okay, let's write just and the distribution of the traits is T close to the distribution of all people in the data. Okay, so what does this mean? It means that, okay, so let's think, I can think of there are these categories of different, has cancer, doesn't have cancer, has diabetes, not have cancer. I can think of this as a one-hot encoding of a vector of all these private traits that I want to release to study the co-occurrence of these, for instance. And so within each group of K class, I want to ensure that the distribution of traits within here is within some, say, Jacquard distance, or kind of some way of measuring the maybe the cosine distance of the average of the whole data set. It can't be too far away. I don't want this to be an extreme kind of category, because then it would say, well, I know something about this category, and I don't know yet whether that's good or bad, right? It could be cancer or diabetes. They're both bad, so I learned that about everyone in this group. Okay, so it's great, but you know, of all the groups you've taken this data and you've divided it down into these groups, and you ensure that each group now is big enough, and they have different classes within them, and that they're each close enough to the full population. What sort of analysis can you now do on this data? You can still do some analysis, you can still make some predictions, you can still show some co-occurrences of various things, but this has been has been sacrificed. And this doesn't necessarily prevent everything either, right? There are these other issues that, I think I've anonymized everything, but like still maybe I haven't. Okay, so what if I have another data set which I was able to align with this and figure out some other information? There are all these kind of attacks on these like releases of data. Right. So let me say one more kind of example, and then we'll try and come back to this one a little bit. So this is a very kind of important thing to think about: the height of Sylvester Stallone. All right, so if you look this up on the internet, it's actually pretty interesting. There's a lot of different information out there about the height of like Sylvester Stallone. It turns out that like lots of movie stars are not as tall as you think they are, and he's possibly one of them. Reports, if you look at reports, they're anything from 5'4" up to like 6'1". For reports on his height. There are websites that just talk about heights of celebrities and try and guess about this. With Sylvester Stallone, there's been a lot of investigation of this. There's some indication that his height has changed over the years, maybe different shoes he wears, maybe he's had a surgery to add 2 inches somehow by elongating his bones. This is apparently a kind of a closely held secret, and in movies they'll film them in certain ways, so it's not clear what was his actual height. But you could think of releasing, if you release, and so every time you take a picture of him, right, in public, right, you're releasing some information about this, right? In a movie, they can maybe guard this, but if you walk down public, you take a picture, you're releasing some information, right? So if you release some information, so Sly Stallone is, the height of kind of the average, so like New Jersey man, right? That's not a question mark. Okay, so let's say I released some information. Maybe I did accidentally, right? There was a crowd of men in like New Jersey, maybe at the beach, and he's there, and he's about the average height. Okay, so I can't really tell how tall he is, but I can tell he's about the average height in this crowd, right? Well, then it's always possible to do a kind of so I can get this independent survey. Okay, so that says that the average height of like men in like New Jersey is so is like 5 feet 8 inches. Okay, so if this is released independently, then this first information is giving away his actual height, right? So it's kind of hard to know kind of what any information release, how is this going to kind of, there could be other information gathered even years later, which uncovers the information you're trying to hide. So this is like so like is like a tricky problem. Let's say I did the Canon Emma T, L diversity, and T closeness, and the governor's information was hidden. But then I'm a reporter. I'm really trying to figure this out. So I call up everyone inside of that zip code who could have been the governor, but wasn't the governor, and ask them for their information, right? And they are willing to tell me something, and I trust them. And so then by process of elimination, I now know the information of the governor, right? So this, if this becomes out there, then there's nothing I can do, right? So there's always kind of like these attacks you can try and do, and the question is how what can we do else to try and, what are different perspectives on this? All right, so before I get into this approach to differential privacy, I want to tell one more kind of story about data. So there was this, so hopefully many of you have heard of this like Netflix prize. So this is back in the day when there was still Blockbuster, and Netflix was this kind of startup that was kind of mailing out DVDs in the mail. Maybe some of you don't know what DVDs are. There are these discs that have movies printed on them, and you had to physically insert them into a machine, and they spun really fast. And then through the magic of hardware and lasers, they showed the movie on your TV. Not in totally high quality, but it was pretty good at the time. And so around 2006, they were trying to, one advantage they had over Blockbuster is that in addition to having a bigger selection of things, much bigger than they have now, by the way, because it was much easier to buy DVDs and send them out than to allow streaming of them. That they released this data set that had the user ID, the movie, a grade that you gave, like 1 to 5 stars, back when people actually kind of did ratings of what they like shows or not, and the actual date that they gave that grade. Okay, and then they had another data set, D2, right? So there's D1 had kind of all this information, and then D2 had but no grades. So I could use the order I watched them in using the date, for instance, and I wanted to try and predict how much they were going to like that movie at that point in time. Okay, so I probably watch like I'm more likely to watch a sequel of a movie after the original, right? I guess I'm more likely to watch Toy Story 3 after I watch Toy Story 2, maybe. I don't know if that's a good example, but you might watch the Avengers movies in order. You're more likely to watch those kind of in order. All right, so and then they had another similar data set D3, which they held back that they internally evaluate things like, and this was like one of the first challenges for Kaggle, where they said, we want to get some good thing, and they said if you could do certain improvement over our prediction that they had their internal system on data set D3, then they would give them, and they had like a year to do this when it was open, they would give the Wayne team like $1 million, right? And so this was, at the time, this created a huge amount of excitement. A lot of top researchers around the world kind of were all working on the problem. Now Kaggle, you'll get some people working a lot more, students work on them than kind of the top people at Research Lab. The ultimate winning team was a group of researchers from AT&T Research, which was one of the top research labs at the time, and maybe a university in Canada. They eventually teamed up, and this led to a lot of excitement in research and cool research. A lot of the ideas on how to effectively build independent prediction engines and kind of merge them together to kind of make an even better kind of like predictor, like really came out of this work. There's a lot of cool work that this generated. Okay, but as this was coming out, some people realized that another big source of ratings of movies was the Internet Movie Database. Okay, and so you know, I know of IMDb. I'll look up stuff on it, and it has their own ratings of movies. These, to do ratings, you apparently need to log in with the user ID and say publicly, effectively, who you are, maybe an email address, and usually that was identifying in some way. And so people rated these movies, and they usually gave about the same you know, had some timestamp on when they did the rating of the movie. Okay, and this timestamp turned out to be important. Just using the IDs, so no two similar people rated movies about the same time, because you probably rate it pretty soon after you watch it, they could actually identify a large number of the users in the Netflix challenge. Even though it seems like, okay, there's not that much information is released, because of the date of the rating, they were able to uncover, you know, I don't think it was with full confidence everyone, but I think with like very, very high certainty, at least 30 to 40% of people, and some certainty kind of close to 80 or 90% of the people, right? And so they could cross these two data sets and kind of identify a lot of the people in the Netflix challenge. The people who rated tend to watch a lot of movies, and they tended to, you know, if they rated on one, they'd probably rate them on the other. If you're watching a lot of movies on IMDb, you probably were a Netflix subscriber, because that's how you could get the most movies at the time. And maybe you watch the movies on Netflix you're embarrassed to put in IMDb about, you know, that you're watching rating all these sports documentaries. You don't want people to know that you also like kind of these high school coming of age movies, right? You would be embarrassed about that, but it was so like your guilty pleasure, right? So some people were not happy about this, and there was actually a class action lawsuit against Netflix because of this. It was later dropped, but you know, a bunch of people got together and said, hey, you have released information, you know, people are able to uncover which movies I liked and rated on Netflix, and I did not give you permission to do this. And so this, you know, there was a lot of great publicity that Netflix got out of this challenge, and eventually a team, I think they're supposed to get 10% improvement, they got 9.8% improvement. I think they still gave them the money anyways, but they got a lot out of it. But then there was this lawsuit, right? So one of the unfortunate consequences is Netflix had this sequel prize that they were planning with a huge, much bigger data set that would have, and you know, eventually this was dropped. They announced it. There was going to be a lot of people who were excited to work on this. It was going to be a really rich, really cool data set to work with, but they dropped it because of the privacy concerns. Right. All right. Okay. So kind of, you can kind of imagine how this stuff happens. Now companies are much more careful about releasing this sort of information, and you know, probably to some extent, I mean, very, very kind of rightly so. You can still get it, but if you want to, you often need to work with a company, sign a non-disclosure agreement, and or they'll release it very carefully in various ways. All right. So okay. So in the last 20 minutes or so, 20, 25 minutes, let's talk about kind of the modern approach to this called differential. So privacy. And this is basically, instead of a more combinatorial database view of this, it's more of a statistical view of how to quantify the amount of information in data that you're releasing. Okay, and so so I'm going to try and it's kind of a, because it's a concept, it's not necessarily an algorithm, and we'll talk about some like very simple algorithms to do it, but it's a bit hard to kind of wrap your head around. I think you roughly now understand the issue, right? So I want to think of having think of having two kind of similar data sets. Okay, let's say D1 and so D2 and think of like one of them, D1 is the real data set and D2 is the one that's actually released, right? So instead of kind of aggregating things together, I'm going to release a data set that's going to look as close to D1 as possible. I want to have two kind of properties. I want that some global analysis on D1 is going to be similar to on D2, right? So if I built a model on them, right, I build a predictive model on D1 or on D2, they're going to have roughly similar results on these models, okay? And that two, say, given a, let's say, given, but for no, particular data point in D1, can I know its value? Okay, so think of this as with the Netflix challenge. I've released the data set of all these users' kind of information. It's been scrubbed of the IDs. I've released this as D2, maybe with some corruption on the data in some way, right? I've manipulated, perturbed it a little bit. So the big picture is still the same. There's no prediction engine I'm going to get by the researchers spending countless hours trying to do well on this is going to be roughly the same, but I can no way of telling if I ask my particular data point what my ratings were, I'm not going to get back my actual ratings. Someone can't look at, even if they identify this is my data point in there, they don't actually know what my ratings were, or they don't know if my ratings, or they can't know if my ratings were in the data set. Sometimes just knowledge that I was rating movies or that I watched a movie is already information. So they may not even be able to know I watched the movie. You have to, so depend on different sort of guarantees, you have these different sort of specific formulations. But the big idea is the global analysis between, let's say this one is this is the true one, and this one is released. Then I want the global analysis to be approximately the same, but the individual data points to be hidden in some way. Okay, so that's kind of the big picture of what's going on. And more specifically, it depends on what do I mean with respect to okay, so what do I mean with respect to global analysis? So with respect to global analysis, you can think of building a regression model, for instance, then asking a query. That'd be one way of particular doing that. That regression analysis would not change too much depending on kind of any individual data point, but it's often asked with respect to a like the original formulation. We're often respect to like some database. Did I watch a movie or not? Right. So think of kind of a data set, and this is user 1, user 2. This is movie J. So did I watch the Twilight series? Right. So user 3. Up to user N. And I just have one they watched, these people watched, and I have these bits inside of here. Okay. And so 1 is they watch, 0 is that they didn't watch. Okay, and so then so remember this was like D1, and so this is going to be D2. Okay, so and I want to ask queries, right? So I want to somehow ask a query. Let's look at this subset of people. They don't necessarily have to be contiguous. So I look at a query. So I look at this subset of people and I add up the true number. It's 1. There are 3 people. So the answer is 3. 3 people in this subset watched Twilight, right? And the other people didn't, right? So this would be an example of a query. And so I want to ask, say, so an example question is, was this query of this, let's say a subset of these users, was this query larger than 4? Was Q of D1 larger than 4? Okay, and let's say greater or equal than 4. The answer is 3, so that turns out not to be true. So kind of there are a couple of strategies for here, but there are going to be some. Do a random process, and I'm not going to tell the users what that. I'll tell them what the process was, but not where I ended the randomness into the process. Okay, so ultimately, I'm going to get a probability. You might actually work with likelihoods, but let's say the probability of the data set in some range, let's say greater than 4. And I want to look at the probability so compared to D1 versus D2 here. Okay, so I could, maybe I can ask this, I get the answer on D2, and I want to know the ratio of these probabilities. Okay, I want to approximately preserve this. Okay, the reason for this is, let's say I asked a really big query, is this bigger than 2, right? Let's say the query was the entire strip. I say, is this have more than 2 people watch Twilight? Of course, more than 2 people watch Twilight, so they're both going to be true, but I want to know the ratio of them if that's changed. This is what's known as, these are likelihoods instead of probability. This is known as the likelihood ratio. And for instance, if the likelihood ratio is greater than 19, that corresponds with like a p-value of roughly 0.05 or 95% confidence, right? So think of if this is, if the probability this is true is 95 and that 5 is true, then you're 95% confident that given a result that I do see something bigger than 4, that I'm in case D1 and the true data set has this, but the hidden one does not have this. And this is great. And I can distinguish the 2 data sets, maybe with 95% confidence. That's okay. So, but typically I want to say this for if for any query, I want this to be this ratio to be about the same. Okay. If it is going to be big on one, I want it to be about big on the other. Okay. And so I want, typically the bound I get is for any query, for any query in some family of queries I'm allowed to ask. I may restrict this. Typically they write this as x, which is e to the power epsilon, right? This is some error tolerance, and let's say this is, e.g., let's say epsilon equals 0.1. So I can allow 10% percentage error, and this exp to the epsilon maybe look a little weird. It's approximately 1 plus epsilon. Okay, so for small values of epsilon, this is really good approximation of 1 plus epsilon. So I'm getting, it's no more than 10% worse in one direction, the probability I get something after I put in randomness. So for any query I ask, the probability that something is true is the ratio of that, even if it's really high, they're both really high. If it's low, they're both really low. The ratio is not off by more than 10%. I can't have high confidence about kind of distinguishing these two data sets. That's kind of the rationale behind differential privacy. Okay, so this is kind of the big picture. This is typically how it's formulated. There's a couple of other, before I go into some more specific examples and how you kind of ensure this, I want to specify a couple other things. There are two versions of this, two versions that are studied. So one is the interactive version, okay? And I'll give examples of both of these. And this, this says I control D1 and D2, right? So I know it, the company allows it, and I limit the queries. Someone asks me a question, a query to my database, and I return the answer. So then I process the query, I return the answer with some sort of noise. Okay, and so you could think of doing this as I fixed the noisy data set D2, so it's D2 ahead of time. But if remember, I have D1, and then D2 is here. And so let's say I ask two queries. I ask, this is query 1, and this is query 2, and there's one data point which is in between. Okay, well then I can look at the difference between query 1 and query 2, and I can maybe infer something about this data point in between, right? Or if I ask enough of these of different sizes, I take the difference between them, I can maybe infer something about individual data points in this way, if I'm not careful about what's going on. And so an interactive user can ask these queries in a way that trying to, I can piece them back together and recover information. So the strategy of the interactive version is I change kind of, I kind of change D2 as I go. I keep it consistent with the answers I've given before, so it's have a fixed amount of noise tolerance in it. And so I know that the analysis, the overall downstream analysis, every query ask is going to be fine. And I know that the noise I've added is consistent, but I also keep adjusting it so that they can't piece them together in some way to uncover these individual data points. Okay, so this is, this allows users to ask much more and get much more refinement on the questions they ask and to do much better analysis. But for the person who controls the database, requires a lot more computation to actually figure out how I can add noise without revealing information. And it's harder and more challenging how to actually do this. Okay, so this is one way of thinking about this differential privacy. And I think the census, so the census this year that's being gathered, or was mostly just gathered, hopefully you all turned in your census forms. If not, go online now, it's probably still open. But you're supposed to have done it already. Then they're going to release the data with differential privacy in a certain way. They're going to allow people to interact it, but in some type of interactive way. Okay, so the other way is the interactive. Okay, and so with this is I perturb D1 to D2, and then I just release D2. I completely release data set D2. Okay, and then users can do anything they want to D2, and I ensure you can't you can't recover any individual, knowingly recover individual attributes of D2. Okay, and so this is typically done where D2 equals D1 plus some Laplacian noise. Okay, so, you know, Laplace noise. So I'm going to add some noise onto D1. I tell everyone I'm adding noise onto this data set before I'm releasing it. And so you don't know what the true answers are because I've added noise to everything, right? So for instance, for movies, I would, you know, it's not Laplacian noise. I'll give an example of that next, but for in a database with things in there or not, you would sometimes sometimes add in things that were not actually watched, and sometimes remove things that were watched. You hope queries on average would do well, but there'd be some information missing and other information adding, so everyone has plausible deniability in some way. For instance, they could say the probability that I've watched this movie is you only know that up to 80% confidence, not 95% confidence. There was maybe a 20% chance that any point in there was added, and any point that if I had it in there, 20% chance it was removed, right? And so you have some deniability, and you can't say with any high confidence that I'd actually watched the movie. If you look at the example with the height of Sly Stallone, okay, so I think it's 2 L's, but maybe I'm wrong there. Okay, so let's say that D2, which is what I've released with noise, I say that this 5 feet and so is going to be 5 feet 9 inches, right? So this is 69 inches, just easier to think about as a single value. Okay, so this is what I've released, and I've said I've released it with certain amount of Laplacian noise. This is equal to D1, which is the true height, which I don't know, plus Laplacian noise with some parameter alpha. And if you remember, Laplacian is a distribution. It's kind of like a Gaussian distribution, but it's peaked like this instead. Gaussian is more rounded at the top, and it's basically e to the negative alpha, right? That's normalized in some way, but it decays instead of e to the negative alpha squared, like a Gaussian, it's e to the negative absolute value of alpha. Yeah, so this is the Laplacian noise I've added to it. So let's say I don't know if the true height was here, if this was D1 or this was D1, but I've released 69 inches as the height. So that's the most likely scenario, and could have been zero noise, but it was something off there, and I don't know what the true answer was. Is that covered in the video? Let me see if that's covered or not. Okay, yeah, you can still see that. Okay. Okay, so how do we think about this from the perspective of differential privacy? I want to know the probability that D1 is greater than 70 inches, so 5 feet 10, right? So maybe Schwarzenegger is 5 feet 10, or I think that what is the probability that Stallone is as tall as like Schwarzenegger? Okay, so let's say, for instance, for example, let's say, I'm not necessarily claiming this, but let's say D1 is actually 68 inches, the average height of like New Jersey man or something like that. Okay, so now the probability of it being greater than 70 is approximately, with Laplacian noise, is e to the negative, let's say a Laplacian noise where alpha is going to be e to the negative yeah, so is e to the negative 2 epsilon, okay, or 2 alpha. Alpha Laplacian noise. That's my parameter there. Okay, so e to the negative 2 alpha, that tells me how fast it's decaying. Because those actually 60 inches, I'm off by 2. So that's the likelihoods or probability that you have it normalized. We're taking the ratio, so we don't need to normalize, and the probability of D2 greater than 70 inches is going to be e to the negative is proportional to 1 alpha, because I release 69 inches. Okay, so what is the ratio of these two things? Let's take the ratio of these two. It's the ratio of these two values of the Laplacian noise. This is equal to e to the negative 2 alpha. So times e to the negative alpha, okay, which is equal e to the negative 2 alpha plus alpha, which is e to the negative alpha. Okay. So if I ignore, if I'd flip these around the other direction, so that means that, you know, you typically go the other way, so it matches up. D1 greater equals 70. I've just put D1 in the denominator instead. This is e to the alpha instead. Okay, it's a positive value, right? And so if I set which is approximately equal to 1 plus alpha, right? If alpha is epsilon, I talked about this before, so I get this guarantee that I get this 1 plus epsilon guarantee on the ratio of these things with Laplacian noise instead. Okay, so this kind of and this Laplacian noise is very nice in that any kind of cutoff, I'm going to get exactly the same ratio here. The math you kind of see an example of it, but it always works out this nice way. So typically Laplacian noise is used instead of Gaussian noise. You get other guarantees with Gaussian noise, but they're nicer with Laplacian noise. And so I'd say that this release satisfies epsilon differential privacy for these sorts of queries. Okay, so there's kind of another example I kind of talked about with the database queries already. You can get this by adding data with a certain probability to also guarantee some similar form of epsilon differential privacy. And you can do that in the interactive as other challenges I won't get into. The basic idea is, just to wrap stuff up here, is that, you know, as I add more noise into the data, I get more privacy, but it's less informative in the sort of queries I get. I'm less accurate in my analysis. And differential privacy is a way of describing this trade-off. And then there are mechanisms you can study that satisfy these privacy guarantees. And so sometimes this actually works. They're using it, apparently, some version, simple version with, I think, Laplacian noise inside the Apple. And they're currently working on how to do this for the US Census. And this is, there are laws mandating they have to release certain information, and there are laws mandating they can't release other information. And they're collecting, and they're not totally sure whether they can satisfy all the laws yet. But this will be decided in the courts over the next few years. This is some fun thing to kind of pay attention to, I guess. Hopefully this will be a fun outcome and not a very sad outcome. Okay, so great. We'll stop there, and we'll talk about kind of graphs and social networks, starting with Markov chains, which provides the kind of the foundational basis for it, and we'll tie things together with eigenvectors again. Okay, that'll be on Wednesday. All right, so we'll stop the lecture here, but I'll stay online for questions.